All right. So hi guys. So I hope you guys had a decent Saturday, and now we're here to ruin it. No, yeah. So welcome to the complex numbers lecture. There'll be a two-part lecture. For now, already depends on if we need a third one to cover the remaining examples. If even if we need to, I guess we'll transfer it to, let's say, another form. We need not let's say do it as a lecture again. All right. So nonetheless, we are part of Inkie Learning. Next slide. Yeah. So this is our vision. So it's by JC graduates. So we have graduated recently. Most of Inkie has graduated last year. I'm the only one that graduated 2 years ago. So it's by students for students, right? It's for all of you here. And the idea is that we want to collate an event useful materials, be it additional questions or maybe notes as well, and have it available for you guys. Alongside that, we want to organize more, let's say, these type of webinars, other educational activities, right? So do stay tuned for our upcoming activities. It's gonna be sort of an exciting August for Inky site, and also unfortunately not so exciting for the J2 site because you guys will be having your prelims very soon. All right, so let's just introduce ourselves. So I'm asmollizard. That I think you guys know that that's actually not my real name, but I go by that as an alias to protect my identity. And for me, I graduated in 2019, as I mentioned earlier. I took further math, chem, and econs, and I'll be going to London to study math and stats next year because I'm still currently serving NS. All right, over to you, Zach.
Right, yes. Hi, my name's Zach. I'm 19 this year, so I actually just graduated last year. I'm currently in NS, and I took PCME. I was from Raffles, and yeah, basically, I'm also just here, to share some knowledge with you. Of course, you please pardon us midway through the lectures if we ever make any mistakes, cause when you guys get to NS, you understand that brain rot is a real thing. Okay, so if we don't ever make any mistakes, I believe Lizard will call me out on it. But if you all actually catch us making any mistakes, please do let us know. Other than that, I hope that you guys will find this lecture helpful, especially for those who are struggling with complex numbers. Yep. And there's a necklace meerkat, by the way. You guys are wondering what that is. Yeah.
All right,
Next.
so before we start the lecture proper, if you guys have any questions at any point of time, feel free to just send it immediately. All right, because we want you guys to be able to keep up and understand the content before we move on to more of the other stuff as well. All right, because this part of the lecture, right, this introduction part, is the most important part in complex numbers because it is the fundamental theory of complex numbers that's going to see you through surviving all the random questions that you're going to get, be it in your promos, if you have learned complex numbers in J1, or your prelims, even your A levels. All right. So we're here to share some crucial tips and techniques and even some cheats if we have the time. All right. So if not, we'll start this proper. Zach, all the best.
All right. Okay. Thank you. So basically now we will start with the introduction to complex numbers. Basically what they are, how they came about, and how and like some traits by which you can identify what complex numbers are. So as Lizard mentioned just now, it's important to learn the basics because especially for math, the basics can go a long way into helping you do well for your exams. Especially because using the basics, you can basically form a train of thought that will help you lead to very smooth and seamless answering of questions. Yeah. So now let's recall about this the discriminant equation that we've learned from secondary school from solving quadratic formulas. All right. Basically, a lot of us when we were doing a quadratic formula, we were faced with very how to say interesting scenario where we get b squared minus 4ac lesser than 0, and then you get a negative number within the square root of the quadratic formula solution. And this doesn't give you a real number, so most of the time, we'll just end up bracketing a reject next to the answer and then being done with it. And so when we get a negative number within the b squared minus 4ac square root, we know that it doesn't give us a real number solution, because when you square any real number, it always is positive. So what do we do about that then? So basically, mathematicians, being very genius people, they created a concept known as imaginary numbers, which is basically what you are learning now, I, which is equivalent to the square root of -1. Yeah, and then this is basically the start of your journey into imaginary numbers, or we like to call complex numbers, because it can be a mix of both real and imaginary when you write them out. Alright, so this is basically the most common form of complex numbers that you ever meet. Alright, x plus yi. This is what we call the Cartesian form of representing complex numbers. Alright, now for the reason why we put it as x plus yi, as we'll learn later, is because you can actually represent these complex numbers in a diagram called the Argand diagram. So we put x to represent the real part of the complex number, and y to represent the imaginary part of the complex number, and that will translate into the different axes on your Argand diagram, which will show you later in the subsequent slides. All right, so not to worry about that first. Also, important thing to note is that x and y are always real. So as you can see the example that we've given at the bottom, z equals to 1 plus 3i. So 1 will be the real part of your complex number, and 3 will be the imaginary part of your complex number. So basically, the imaginary part of the complex number is sort of the coefficient of I, where I represents the square root of -1. So you can think of it in that way also. All right. So first, we'll start off with introducing you to some simple identities which you can use for complex numbers. All right. So as I said before, I is square root of -1. So just like how you would solve a regular square root, if I equals to -1, if you square this, you get -1. If you square I, you get -1. So if I square equals to -1, I cube equals to -1 times I, which will give you -I. All right. So it's basically putting into practice your general indices rule, if you know what I mean. So I square equals to -1, and then you get I to the power of 4 is equals to I square, and then you further bracket it, square. So like you see there, I square is actually -1, and if you square -1, as with all negative numbered squares, you get a positive number. So I to the power of 4 will be 1. Very simple. Okay. All right. Next. And now we come to multiplication of your complex numbers. And this will just be the general. This will be very easy because it just follows the same rainbow method that you guys should be very familiar with. Basically, when you get this a plus bi bracket times c plus di bracket, it will just be a times c, a times di, then bi times c, then bi times di. But a point to note is that when you multiply the imaginary parts of the two complex numbers, you get an I square. So you actually find that BDI square will give you an eventual negative BD, as you see here. Okay, so this is something that you have to take very careful note about, because a lot of people actually make many careless mistakes when doing multiplication of complex numbers. All right. Okay, next. Here we go. When you get identity such as this, z over I, just like how you would rationalize an irrational number, so to speak. Like, let's say you get a 1 over root 3, you can do almost the same thing for your imaginary numbers. So you just multiply the top and bottom by I. The bottom, as you said before, will give you an I square. So this will give you a -1, and the top will be I times Z. So the resultant number that you get is negative IZ. Alright. Next. Okay, we're gonna talk about the conjugates of your complex numbers. So let's say you are given a complex number such as Z. Sorry. Let's say they give you a complex number such as Z equals to 1 plus 3i. So Z conjugate will be 1 minus 3i. So what a conjugate means is that the sign of the imaginary part of your complex number will be flipped. So as you can see, if Z equals to A plus BI, then Z conjugate will be equals to A minus BI. And if Z is equals to A minus BI, then your Z conjugate will be A plus BI. Okay, this is very important as it will be very useful later on when you solve questions. And also because examiners like to play around with all these different concepts that they have taught you. Okay. So now we go to the multiplication of your complex number with its conjugate. Okay. Basically, it will give you a resultant answer of a square plus b square. All right. So let me explain further. If z, hold on. If z equals to a plus bi, then your z conjugate will be equals to a minus bi, right? As you see there. So basically what this will give us is, as you all know from expansion and simplification topic you learned in secondary school, it will give you a resultant of this, alright, in the form a square minus b square. But then because your I is squared, this part of the equation, of the expression, will give you a negative b. So eventually you have a square minus negative b. And minus negative will give you a positive. So a square plus b square. Also another very important concept to know, because it will help you to pick up the pace on your complex number multiplications in the subsequent questions that you attempt. So basically, if you have a complex number z multiplied by its conjugate, it will always give you a real number. So yeah, as I said just now, it will be quite useful when you try to simplify an expression. All right, so now I'll give you guys about, let's say, 5 minutes to try and attempt these two questions, and then I'll come back in to check up on you guys. All right, so your 5 minutes start now. Okay, I'm just gonna cut the time here because I realized that 5 minutes for these two questions might be a bit too long for you guys. Alright, so let's go through the questions now, okay? So basically, for the more discerning of people who are attending this lecture, so not a lot of y'all lah. Basically, when you see these kind of questions, most of your teachers will actually tell you, just press GC, which is what you can do. This is how you use the GC. Alright, and then you get this answer. Only problem with it though is that as you see the question that we gave you is to express 1 plus 3, especially for question 2, you're supposed to express 1 plus 3i over 2 minus 5i exactly. But you see the answer that the GC gives you is an irrational number. Alright? It will work for the first question, but for the second part it won't work because you have to give it in terms of fractions. Yeah. Okay, so going back, I'll now go through how you do this manual method lah. Okay, so this is how I like to do it, but you guys might have a different method of doing it. So I like to take things slow and steady. Some of you might remember the exact formula for cubing your identities. So you guys can go ahead and use that, no problem. But for me, because I like to see my working and actually take note of how I'm doing things, what I like to do is I take 2 plus I and I square it first. Then I multiply the answer with another 2 plus I. So once you do that, after the expansion of 2 plus I, you get 3 plus 4i. And then you multiply this by 2 plus I. Which will give you the final answer after you simplify the expansion to 2 plus 11i. Okay, simple. At this point in time, if you have trouble doing this sort of simple expansion and simplification of the complex numbers, is very important that you start to practice doing it now. But I would assume that most of you wouldn't have too much trouble with this because it's actually very similar to the regular algebraic expansion of your algebraic expansion of your identities to the power of 3. Okay, so I won't comment too much about this anymore. Next, you will have the 1 plus 3i over 2 minus 5i. Okay, so how I like to do it is you multiply the top and bottom with 2 minus 5i. Okay, like I said just 2 plus 5i, sorry. Like I said just now, it's basically multiplying the top and bottom with the conjugate of 2 minus 5i. Okay, so as you can see, this is a very useful, the conjugate, the idea of multiplying the complex number with its conjugate is a very useful thing because sorry,
Your denominator.
yeah, sorry.
Oof.
It's very useful, as I said just now. Okay, sorry about that. Okay, yeah. Okay. So as I said, it is very useful in helping you to solve these kind of questions, especially because you want to sort of rationalize the bottom, like how you do it for your square root. Okay, so from here, what do you get is basically 1 plus 3i bracket 2 plus 5i over 2 square minus 5i square. Okay, so I'll solve the denominator first, okay, just to show you guys how it's done. What you get is 4 minus negative 25, because as we said just now, when you square I, you get negative 1. So this identity over here will become negative 25. So minus negative 25 will give you plus. So it's 4 plus 25, which will give you 29. And then the numerator, if you slowly solve it, you get negative 13 plus 11i. Okay. Now, a lot of schools will suggest that you strictly stick to this form. Okay. And I will also recommend that you present your answer in this form. So what we're gonna do is you're gonna write it out as 1 over 13 over 29 negative 13 over 29 plus 11 over 29i. Okay, that's how you do it. Okay, very simple. Shouldn't be too hard for you guys. Huh? Very, very foundational ideas, but very important because you will definitely be using it in most of your complex number questions. Okay, let's move on. Okay, for this one, I'll show you guys first how to solve this question. Then I'll proceed on to give you the next question for you to solve. Okay. So now we see we have a quadratic equation right here. But as you all know, some quadratic equations cannot be solved. Won't give you a real number. They'll give you complex numbers, because when you check the discriminant of this quadratic equation, it will actually give you a negative discriminant, and that's where you derive your negative number from. That's where you derive your imaginary number from. Sorry. So you're just gonna solve this as we do with any quadratic equation. Okay, you can't use the I don't know what you call it, the one where you draw the
Cross method.
Yeah, cross method. Yeah. Sorry, I can't remember the exact name. Okay. So what we just do it, we just use the quadratic equation that we know, which is x equals to negative b plus minus square root, of b square minus 4ac over 2a. For the 2a, still got a lot of people, even in JC, will forget one. So watch out about that. So you just submit out your values, you simplify it to 4 plus minus square root of 16 minus 4 bracket 1 bracket 5 over 2. Then you will simplify this down until you get 4 plus minus square root of -4 over 2. Okay, for those of you who haven't noticed yet, okay, how you write out this part of the simplification is, how we're going to look at it now is, you get square root of negative 4 equals to square root of 4 times square root of negative 1. As I said earlier, I equals to negative 1. So you get square root of 4, which is equals to 2i. So this will give you 2i. So now you get 4 plus minus 2i over 2. So the possible roots of x will be 2 plus I or 2 minus I. Okay? Yes, very simple. It's basically how you solve your quadratic equations, except that when you see that b squared minus 4ac is lesser than 0, you don't just stop there and reject x. You continue all the way because somehow this part will be reduced down to give you an imaginary number. Okay? So you just continue all the way. Alright, so the next question that will have you try is this. Okay, I'll give you about I'll give you about 2 minutes to solve this. I think that should be enough time. Okay, your 2 minutes start. Okay, I think in the interest of time, we'll just stop here. Then I will go through the question now. Basically, right, guys, I think most of y'all will already know when you get polynomials, right? Your math tutor will also tell you to just press GC. Okay, so for those of you who don't know how to find the polynomial equation solver on your GC, basically you go to applications and then you press 4, or you use the arrow button to locate all the way to polysimultaneous number 4, as you can see over here. Okay, then after that you set the settings to the index of the highest variable in your polynomial. Yeah, so the one we gave you just now was a quadratic equation, so the order is 2. Then you just fill in everything, and then like just now I showed you guys, for the first one you get 2 plus I and 2 minus I.
Before you guys click solve, you guys need to change it to from real to the a plus bi. Otherwise, you guys won't get any imaginary or complex roots. All right, so take note of that as well.
Yeah. Okay, so I'll just go through this fast one Okay, sorry. So your x will, like we did just now, like we did just now, use your quadratic equation. I'll just speed run this so you get, eventually you get 4 plus minus 6i over 2. So you get 2 plus minus 3i. Okay, very simple. Just follow all the steps that you will normally follow for solving a quadratic equation using the x equals to negative b plus minus square root of b squared minus 4ac over 2a. Yeah, then you get the answer. Okay, then we'll move on to a more complex form of solving polynomials, where you have coefficients of complex numbers here. Okay, so like just now, I'll attempt the first example first, then I'll give you some time to try on the next example. Okay, so basically same thing again, you try and solve it using the quadratic equation that you know. So instead of subbing So you just follow through. You sub in the coefficient of the complex numbers. Similarly, okay, x equals to 2 minus I plus minus square root of 2 minus I square, because you square a negative, you get a positive square, okay? Minus 4 times 1 times 3 minus I. Okay, and same thing 2. So when you expand this out, right, you realize that the imaginary numbers that you produce, the imaginary numbers that you produce will basically cancel each other out. So when you expand it out, your 2 minus I will give you 4 minus 4i minus 1. And then the second part of the equation, where you get the 4 times 1 times 3 minus I, you get a negative 12 plus 4i. Okay, so since you get negative 4i and a plus 4i, those two will cancel each other out. So eventually you get inside the square root, it will be 4 minus 1 minus 12. So you will get a negative 9. Okay, so it will reduce down to 2 minus I plus minus square root of negative 9 over 2. So like I said earlier, this will give you 3i when you simplify it further. So it's 2 minus I plus minus 3i over 2. Okay. Now this is a bit different because now you have to consider 2 minus I plus minus 3i. So the variable will be the complex, the imaginary part of the answer. Okay. So eventually your answer when you proceed to solve it will be 1 minus 3i and 1 minus 2i and 1 plus I. Okay, simple. Okay, so I will give you guys time to try out the next example. I think about 1 minute 30 seconds will do also. So I'll check back in later. Okay, time's up. Okay, basically I'll just give you guys the answer. The answer is negative 3 minus I and negative I. Okay, just follow the correct sequence of solving your quadratic equations. You won't go wrong with solving these equations. But one thing to note is that for the square root part, right, where you get a b squared minus 4ac, it won't always perfectly cancel out like how these two questions show. So sometimes you might get an imaginary number within the square root, and then that will be a bit more complicated, but we'll cover that tomorrow. Or you can also just get a perfectly normal real number. So yeah, there are multiple scenarios to this, so there's something just to take note. Okay, but that's a bit more complicated. We'll cover it tomorrow. Okay, yeah, so I think this shouldn't be a problem for you guys. I won't go through it too much because we are kind of running out of time. Okay, so just move on to the next slide. Yeah. Also, you realize that when you are given complex coefficients, you realize you won't be able to input them and solve the quadratic using your GC. So when it comes to quadratic equations or polynomials with complex coefficients, you want to manually solve them lah. Okay. So next, as I was saying at the start, your Cartesian form x plus yi, we put in this form because as you said, as we recall in your regular graph, you have an x and y axis. So x is your horizontal axis, y as your vertical axis. And then on your Argand diagram, which is what we're going to go through now, you realize that the imaginary part is your vertical axis and your real part will be your horizontal axis. So that's why we represent it in terms of x and y when we're writing out a algebraic form of your complex numbers. All right. So, all right, when you have the Argand diagram, you come across two different things. One is your modulus, which is the magnitude of the complex number, and another thing is the argument. Okay. Usually, when you solve your argument, you'll be using tangent to solve it because, as you already read, as some of you might have already realized, you have your z equals to a plus bi or x plus y. So this will correspond to your vertical axis, and then this will correspond to your horizontal axis. So let's say you have a number like 3i plus 3. So you have something like this. Your argument is basically this angle. Okay? Specifically for this quadrant only. Okay? Now, when you're gonna solve for the argument, you realize that you're only given the coordinates on your Argand diagram as the real and imaginary parts of the complex number. So what you're gonna do is, as you know by your Tuakaso, tangent is the opposite over the adjacent. So yeah, as you see here, the basic angle is given by this. All right. Now, sorry, I'll erase all this first. Okay, so as you can see, your Argand diagram looks like a normal graph, but how you read it is different from a regular graph. All right. So for your regular graph, when you're looking at your quadrants, they're all looked at as positive angles. But for your Argand diagram, you realize that the top half will give you positive in terms of radians, and then the bottom half is negative in terms of radians. Okay, but I'll leave that to cover more on later when he goes through the trigonometry part of complex numbers. Okay. So how you calculate your modulus and argument? For your modulus is basically using a Pythagoras theorem, all right? So as you see in your Argand diagram, you are given the coordinates of the vertical and the horizontal. So you just do this. The modulus is basically the hypotenuse of this imaginary triangle that you draw out by connecting this part and this part onto your graph, all right? It can also be this way, or it can also be this way, or it can also be this way. Okay, you get my point. Okay, now the important thing to take note is that your modulus is always positive, even if it's on this side of the quadrant, this side of the quadrant, or this side of the quadrant. It is always positive. Okay, because you won't get a negative square root. All right. Now for your argument, as I said just now, you'll be measuring it from the positive real axis. Okay, so this is an argument when it's in this quadrant. The argument for a complex number when it's in this quadrant will be this. Argument for a complex number when it's in this region will be this. And when it's in this region, it will be this. Okay. Now we will move on. Alright, just some important identities and concepts to take note of when we are looking at modulus and argument. So a complex number will have the same value even if you rotate it around the point by a certain number of times. K is an integer. Okay. So if you, let's say this is the complex number represented on the Argand diagram. If you rotate it by 2 pi, you're basically rotating it like that. So that's the same number. No matter whether you rotate it 3 times, 2 times, 4 times, it will still be the same number, okay? So try and remember this equation. Don't need to memorize it, but understand why it's like that, because in subsequent questions where we show you, which will show you, this is particularly important, okay? So for example, you have so for example, if you have an argument which is outside the principal range, like this, you have to, for me, I like to represent it on the Argand diagram to help myself to see clearer. Okay, so let's say you have a wait, sorry, you can't use an Argand diagram for this. Sorry. Let's say you have a complex number with an argument such as 3 pi over 2. You have to reduce it to within the limits of your principal range to this. Okay, as long as it's greater than pi or it's lesser than negative pi, you have to reduce it back into the principal range. Okay, I will leave more to Lizard to cover that later, alright? Okay, next we'll go through these special triangles. In case some of you haven't already read, still don't remember, you have your special identities with regards to your trigo. Most of you will remember it in terms of degree, but when you're dealing with complex numbers, you always deal with it in terms of radians, okay? So you see this is an isosceles triangle, this is 90 degrees, so these are 45 degrees. Alright, so let's say this is 1, this is 1, this side is 1 cm, this side is 1 cm, this side will be root 2. Okay, so this is 45. Your sine will be your opposite over hypotenuse, which will give you 1 over root 2, which you can simplify to give you root 2 over 2. For your cosine, it will give you 1 over root 2 as well. Okay, so you get root 2 over 2 as well. Okay, yeah. So this is one of the important identities you need to memorize. It's basically a table for most of you. Some of you who don't know what I'm talking about, it's your special trigo identities. Okay. Hold on, let me erase all this. So for the other triangle, you have it in terms of, as you can see, it's a larger angle. This will be 60, and this is 30. Okay. For me, I basically have it memorized in terms of the order of ascension. Okay, so for sine, you have 0, 30, 45, 60, and 90. Then for sine 0, it will be 0. Sine 30, it will be square root of 1 over 2. Then square root of 2 over 2. Then square root of 3 over 2. And then square root of 4 over 2, which will give you 1, basically. Sorry, Okay, then for your cosine, it will just be the reverse of this. So as you can see, for sine, it will be going upwards. For cosine, it will be going downwards. So you'll start with root 4 over 2, which is 1. Then after that, 3, 2, 1, and then 0. For tangent, it will be a bit different. Okay, so tangent, but there's also a pattern to it. Tangent, you'll start with 0, 1 over root 3. 1 root 3 over 1 and then infinity, because as we know tangent 90 is undefined. Yes. Okay. This triangle thing, I won't go too in depth on it. You can draw it out. Let's say you give a number to each side, then you realize that when you put it in terms of sine and cosine, you reduce it down into these values. Okay, but take note, I'm writing all these in degree, but when you're dealing with complex numbers, you're supposed to deal with it in terms of radians. So for 30, it will be pi over 6, 45 will be pi over 4, this will be 60 will be pi over 3, and 90 will be pi over 2. Okay, all right, next. So we'll try this very fast. We'll go through the modulus and argument of this. So I'll just show you guys. Okay, 4 plus 4 times 3. Okay, square roots. Find the modulus. So this will give you 16. This will give you 16, and the square root of 16 is 4. Okay. Next, you find the argument of z. Which will give you tangent inverse x over y, right? As we said just now. So x is your 2 over root 3. 2 times root 3. This will give you 1 over root 3, as I said just now. This will correspond to pi over 6. Okay, right. Next, I'll just show you what this looks like on your Argand diagram very real quick. Okay, so 2, 3, 2. So basically it will look like that. This will be your argument, and this will be your modulus. Okay, this is your coordinates where it's 2, 2 and root 3. Okay, all right, next. Okay, so I'll just show you guys this on the Argand diagram because for me it's better to visualize it on the Argand diagram. Basically, when you see the modulus of the conjugate of z, the modulus with it remains the same. So as we said just now, because this will become a negative, but when you square the negative, it will still give you the same answer as so negative 2 root 3 squared is the same as positive 2 root 3 bracket squared. Okay, so the modulus of z conjugate will be the same. Okay, but for the argument it will be different because now your now the complex number will lie in a different quadrant. Okay, so basically it will be negative 2 and 3 pi. Okay, so this will be your argument. So now your argument is in the negative 2 quadrants of your Argand diagram. This will be negative pi over 6. Okay, if the previous one was a pi over 6, now you have it as negative pi over 6.
Pi over 3.
Oh, sorry, pi over 3. My bad. Okay, so sorry. Yeah. All right. Okay. Okay. Next, we come to this. The modulus will be the same as you can see. Okay, because we just switch the sign of 2, but when you square negative 2, it will be equivalent to square of 2. Okay, so the modulus will be 4 like just now, but now the argument is different. Okay, 2. Yeah, okay, your argument will be here. Okay, so the argument will be this angle. Okay, so how you do it is actually basically you just take pi minus this. So you sorry, I have water to drink. Sorry. Okay, so as we found it just now, right? Your argument for the previous set was tangent inverse x over y. And as the sides written out by Lizard just now showed, tangent negative x over y basically gives you the basic angle. Okay, just ignore the sign for now for now. Okay, basically all the negative numbers, right, we'll just change it to positive, and then we'll look at the magnitude of the length. Okay, not the we look at the magnitude of the numbers, not the sign of the numbers, basically. So basically, you find the basic angle, which is your tangent x over y. Then because you see there's sorry, y over x. I bet.
And as it you hard.
Yeah.
Basically, it's like how you will solve your cosine, sine, like your multiple angles when you are solving like trigonometry. It's basically finding basic angle and then considering the quadrant.
Yes, I forgot about that. So sorry. Thank you. Yeah, so you just take pi because you realize that this is in the top half of the Argand diagram, so everything is positive. So you take pi and then you minus your basic angle, which is tangent y over x. So you refer back to this, is basically 2 root 3 over 2. Okay, so it will be pi minus pi over 3, which will give you 2/3 pi. Okay, that will be the argument for this particular complex number. Okay, let's move on because otherwise Lizard won't have to sleep already. Okay, next we have this one where everything is negative. Okay, so -1 and 2/3 will be here. Okay, now as you can see, the argument for this will be like that. Okay, but since it's in the bottom half, this will be a negative radian. Okay, the argument will be negative. So how you gonna look at it is, hold on. You find your basic angle first again. Tangent y over x. Tangent inverse y over x, which is sorry.
2 root 3, tangent inverse root 3.
Yeah, 2/3. Yeah, basically 2/3 lah. Okay, but there
2
isn't
root
a way
3.
to reduce it, right?
Yeah, there's no way to reduce it. So this is the classic example where your argument will be in the trigonometric form, where it's tangent inverse 2 root 3 over 1. So tangent inverse 2 root 3, which means that you're going to leave your angle both in pi and in the trigonometric form as well. So in this case, I made the sneaky change out from -2 to -1. So you guys need to take note of that. So now your angle would be minus pi plus the basic angle, because now if you go minus pi from the real axis, you'll hit to the negative real axis portion. Then your basic angle would be basically the angle between the x-axis or real axis with the complex number. Yeah, so that is how you get your argument for this particular quadrant.
Yeah, okay, basically what Lizard said. All right. So I think I won't go through the modulus, how to find the modulus again, because it's very self-explanatory. Basically, it's just your Pythagoras theorem to find this hypotenuse of this line we have drawn from your origin. All right. Next, I'll start to hand the time over to Lizard. Basically, what we've covered has mostly been in Cartesian form. Now Lizard will go through the Trigo form. All right, I'm just gonna stop presenting first. Oh, you took over the presentation.
Right, so we're gonna go through this part again. So your basic angle is in tangent form, because now there's really no special angle for your 2 root 3, right? So basically, if you look at your angle, right, you had this point here, right? So this will be your basic angle now, alpha. So from here, you want to find, but then this is your argument. So what we need to do is take from here to here, which is minus pi, then you plus back the alpha because your basic angle is positive. All right, so that's why you will get your argument here will be minus pi plus tangent inverse to root 3. All right, we'll talk about this later on again when we look at the other forms to represent your complex numbers. All right, so the second form to represent your complex numbers, let's just say we have the same complex number at 3, 3. All right, your coordinates also can write inside as well. So this is clearly 3 plus 3i. So you notice that this is a complex number. You have the argument, right? So argument will be this. Okay, and then we know that if I have to draw this as x, and then we have this as y, your modulus, right? We keep seeing as mod z, is actually also equals to r. Now, I think you might have seen this before in your secondary school, where your modulus of a particular point is r. So what do we notice about this? We have the hypotenuse, we have the angle, which means that we can find or express x and y in trigonometry form, right? Because we know that sine theta is opposite over hypotenuse, so we have opposite as x, hypotenuse as r. Rearranging, this gives us r sine theta. Same thing for our y, but now we have the adjacent side as such, we have cosine. So we have y over r equals to cosine theta. Rearranging, we have y equals to r cosine theta. Okay, so this is what we call by the trigonometry form. Okay. The second form, trigo form, as I repeat again, x equals to r cosine theta, y equals to r sine theta, theta equals to tangent inverse y over x, or, really depends, pi minus tangent inverse y over x. This would be your second quadrant, or minus tangent inverse y over x. This will be your fourth quadrant, the cosine quadrant. Otherwise, it will be minus pi plus tangent inverse y over x. Right, this will be your third quadrant. Okay. Even though it's a second form, it's still the same. You'll give the same complex number as your x plus iy. It's just put in differently. All right. So we know here we have x plus iy equals r cosine theta plus ri sine theta or ir sine theta. Then here is missing an I. So r bracket cosine theta plus r sine theta. This will be your trigonometry form. All right, which means one thing. You notice that in your trigonometry form, you only need the r and theta. Right? R being the modulus, theta being the argument. As such, to convert from Cartesian to Trigo form, you just need to find the modulus and the argument, and from there you can obtain the either side, right? Either you can convert from Trigo to Cartesian or from Cartesian to Trigo. Okay. The Trigo form, no, you don't. It's really quite useless, lah. To be very frank with you guys, it's not very used. It's not used a lot in H2 math, but for further math, it's really amazing, right? You get to prove a lot of the different identities. So if you guys are interested, you guys can message me on the Inkie's Discord, or you guys go and redo some research yourself. But then again, you use trigonometry form for some important ideas, which I'll show you guys later on. All right, so some properties of our trigo. The mod of z is simply r. All right, so we had r cosine theta plus I sine theta is basically just r. Why? Because if we were to look at this, it's basically cosine square plus sine square. Then we know that this will give us modulus 1. All right, your trigo identity. Next part, r cosine theta plus I sine theta. Why I added this in is because if you want to check your work, let's say you found the theta, all right, you haven't put in the r yet, right? So you from cosine theta will give you a, sine theta would give you b. To check whether your a and b are right, just put them a squared plus b squared equals to 1, because it's the same idea. A equals to cosine theta, b equals to sine theta, it'll be cosine square plus sine square equals to 1. So that's how you also check your answer. Of course, ultimately, your final complex number would then be AR plus BRI, right? Add in the modulus or the magnitude. Okay, so one more important idea, and I want you guys to take note of this. R may include theta. Your modulus may have a trigonometry identity or a trigonometry, and it wouldn't affect the argument. All right. So the main thing about trigo form, and in fact the next form as well, these two angles must be the same. right? The angle inside cosine theta plus I sine theta must be the same. Okay? As you notice here, we have theta over 2 and theta over 2. So argument is theta over 2. Your modulus is now cosine theta, r bracket cosine theta plus I sine theta. As such, your r is now cosine theta. Your argument is theta over 2. And that's what you guys need to take note. All right. Okay, so let's try some things. Okay, express 2 minus I as r cosine theta plus I sine theta, the Trigo form, where r is bigger than 0 and theta is in the principal range. So very simple. First, find the modulus, where we have the square root sum of squares, right? 2 square plus 1 square will give us root 5, right? 4 plus 1 is 5. So that will be our r. Our theta, now you gotta be careful. What quadrant is this in? 2 minus I, so you can just do a quick sketch. Your real is positive, but your imaginary is negative. So you will be in the 4th quadrant, somewhere around here, which means your angle, your argument will be minus tangent or the negative of your basic angle, so half, right? So minus tangent inverse half. Is there a special angle for this? Answer is no. Okay, so we leave it as our tangent inverse form. But what's the problem? Now we put back the r and cosine theta. All right, so when you put back the theta, you can just use it straight away. So substitute r as root 5, the modulus. Now we have cosine tangent inverse half plus I sine tangent inverse half. Now, why I put this example immediately? Because you cannot leave your trigonometry like this, supposedly. But because the question wants you to leave it like this, go ahead. If not, actually, this is not the proper form, all right, for let's say Cartesian, okay? But since they want it as cosine theta plus I sine theta like this, it's all right to leave it like, or to leave the tangent inverse. Otherwise, you actually need to evaluate cosine tangent inverse and sine tangent inverse half, right, to actually get you back 2 minus 1. That is for the algebraic portion. All right, so do take note, you are not allowed to leave your answers like this, where it's cosine and then another trigonometry inverse inside, unless the question asks you to do so, which in this case, they did. Okay, so just to add in the minus sign, because I left them out by accident. All right, okay, so this is the first example. Very simple, find the modulus, find the angle, you get the trigonometry version. All right, now I give you a slightly easier example, minus 2 plus 2 root 3. Okay, so give you guys about 1 to 1.5 minutes, find the modulus, find the argument, and then write it the trigonometry form. I mean, if you notice, the numbers is basically the same as whatever examples we gave you earlier. So actually, you know what? Just you guys should probably find r very fast, you know it's 4. Okay, now just be careful when finding the argument. So do take note of which quadrant this argument or this complex number is in. Okay, I think I will just give you guys 5 more seconds. I think most of you have already gotten it. Okay, so argument, we know that this complex number is in the 2nd quadrant. All right, because it's negative real, positive imaginary will be this part here, which means that our basic angle, or rather our argument, will be pi minus the basic angle. So find the basic angle, tangent inverse 2 root 3 over 2. So very simple, root 3, which then give us pi over 3. Your argument of this would simply be pi minus pi over 3 equals to 2 pi over 3, aka 120 degrees. Now we express this in our trigonometry form. Modulus is 4, bracket cosine 2 pi over 3 plus I sine 2 pi over 3. All right, as simple as that. Mainly take note of the quadrant. Whenever you're finding argument, all right, you need to take note of the quadrant. Okay, so far so good. If not, I'll move on. Now, again, continue with conversion. This is where I talked about the tangent inverse, right? So they give you the modulus, they give you the argument. So just put in the formula. You know that the form is r cosine theta plus I sine theta. So we put that in. R is basically the modulus. So we have 2. Cosine theta is tangent inverse 3/4 plus I sine tangent inverse 3/4. Okay, we cannot leave it like this because we want to get a plus bi. It is not fully simplified. So what we need to do whenever you get into these cases is simply draw your triangle. All right, you can label this as your theta. You know that tangent inverse 3/4 is given by theta, which means opposite is 3, adjacent is 4. Okay, then now, because you're dealing with cosine and sine, you need the hypotenuse. All right, because I'm familiar with these numbers, the hypotenuse is 5. Alternatively, Pythagoras theorem 3 squared plus 4 squared equals to 9 plus 16 equals to root 25 equals to 5. Okay, so that is how we do it. So which means that is very simple, right? So now we get cosine of this theta. So cosine will be adjacent over hypotenuse 4 over 5 plus I sine tangent inverse 3/4. So sine theta 3 over 5. All right. We then put in the modulus 8 over 5 plus 6 over 5 I. All right. You can also check your work. All right, if you want to check your work here, 4 square plus 5 square, 4 square over 5 square plus 3 square over 5 square equals to 25 over 25, which equals to 1, which means we did our calculations correctly. All right, as I showed you guys just now. Okay, so far so good. Now you guys give it a go. Give you guys a nicer type of number as well. But now take note that we have A and B less than 0. So what quadrant is that in? That's the first thing you take note of. Whenever you're doing complex numbers, take note of the quadrant that the complex number is in. Just now it was in the first quadrant because A and B are positive. Now it is negative. So it is in the third quadrant. That's why the argument is minus tangent inverse 12 over 5 to a certain extent. All right. Anything? Okay, so gonna do this question. We know that modulus of Z is basically your R, so we can start by writing 4. Okay. Now, importantly, because we know that it's in the third quadrant, it must be negative, negative. If we have just simply did this, cosine minus tangent inverse 12 over 5, and then you ultimately converted this to cosine tangent inverse 12 because you use the identity cosine minus theta equals to theta. Cosine minus theta equals to cosine theta. I'm sorry, but this is not right. All right, because now they tell you that A comma B is less than 0. It is in the third quadrant, so this part is also negative. As such, you kind of need to take out the negative sign later on, right? But same thing, because we are dealing with tangent inverse, so we need to draw our favorite rectangle, all right? So you guys have already tried that out. But again, let's just draw the triangle. So we now have our opposite as 12. Let's say we give this as theta. Opposite is 12. Adjacent is 5. The hypotenuse would be 13. All right, because 12 squared plus 5 squared, 144 plus 25 equals to 169. Root 169 would be 13. Okay, now we put in the values and we have to be careful. A and B are less than 0. It's in the third quadrant. So cosine tangent inverse 12 over 5, so cosine theta is originally 5 over 13. So we get minus 5 over 13. Our sine theta is now negative as well because B is negative. Our imaginary part is negative, so minus 12 over 13 I. All right, don't forget the I. This then gives us minus 20 over 13 minus 48 over 13 I. Okay, so that is how you convert from Cartesian to Trigo or Trigo to Cartesian, and take note of A plus B, A and B. Okay, now we move on to the best form for our complex numbers. Why I say it's the best? Because this is really the superb form that gives you all or most of the identities that you need when it comes to applying in the questions tomorrow. All right, so let's begin. Exponential form. All right, exactly the same as your Trigo form, but expressed differently. The exponential form again just needs your modulus and the angle. That's it. You just need two things for exponential: modulus and your argument. Same thing for Trigo, modulus, and angle, or the argument. So we represent the exponential form as z equals to REI theta. All right. So R being your modulus, theta being the angle usually in the principal range, minus pi to pi, inclusive of pi only. All right. And do take note, just like your trigo, R is positive because it is the magnitude. Okay. Superior form, and as I mentioned, helps us derive a lot of identities. And again, like your trigo form, just because it's in another form doesn't mean that it does not equals to the other forms as well. All right, so z equals to RI theta, it is equals to R cosine theta plus I sine theta. It is also equals to x plus I1. All right, so they are all equal, which means that you can convert one to the other. Okay, so we have this equation. How do you convert from one to the other? If you have x plus IY, you just need to find modulus. You need to find the argument. You can get either exponential or the trigonometry, right? So you just need these two things. But if you convert from exponential to Cartesian, you need to go through from here to here, and then from here to here. All right, just basically sub in the theta into here, and then put in your r down here. All right, so from from exponential to your trigonometry, just write the form r cosine theta plus I sine theta with the respective r with the respective theta because they are the same. Okay, then from Trigo, you just need to evaluate. Once you get into this form, you just need to evaluate cosine r cosine theta and r sine theta to give you x and y. All right, so it's quite simple for conversion. And here I talk about special triangles because it's really from the triangles that we've seen just now. Basically, these are the few forms that you should be aware of. Plus minus k plus minus ki, your basic angle is pi over 4, your basic angle is pi over 3, 4 plus k plus minus k root 3. Your basic angle is pi over 6, 4 plus minus k root 3, and plus minus k. All right, these are the few things you should be taking note of. All right, so let's try. I'll show you the first example. Express z equals to 2ei 2 pi 3 in x plus iy. So we have the modulus as 2. So first convert this to Trigo form. So z equals to Trigo form is r cosine theta and I sine theta. Your argument is 2 pi over 3. So cosine 2 pi over 3 plus I sine 2 pi over 3. You need not worry about the quadrant now because the argument will basically tell you which quadrant that your complex number will be in already. All right, cosine 2 pi over 3 is simply half. So you get 1. Plus sine 2 pi over 3 would be root 3 over 2, root 3 over 2 times your modulus, which is 2, you get 1 plus root 3i. All right, wrong. You'll get minus 1 plus root 3i. All right, so take note of your cosine 2 pi over 3. It is minus 1. Okay, so be careful. Your basic trigo evaluation must still be correct. Don't just blindly take the basic angle and then forget to put in your negative or positive. All right, so in a sense, if you are still careless, remind yourself what quadrant this complex number is in. In this case, it's in the second quadrant. Your x is negative, your y is positive. Okay, now have a go at the next question. Express minus 2 plus 3i in exponential form. Now you get a slightly different or difficult answer because now your argument is not in pi, right? You'll be in tangent form. All right, so again, just go ahead and try it out. All right, it's easy, Cartesian to exponential. You just need two things, modulus and the argument. Okay, so modulus should be quite fast, right? Root minus 2 square is same as 2 square, so 2 square is 4. 3 square is 9, so I get root 13. Argument of z, well, be careful. Which quadrant is this in? Second quadrant, which means pi minus the basic angle, tangent inverse 3 over 2. Okay, so now we just put in exponential form. Very simple. Z equals to, put your modulus, r EI theta, which is the argument. So pi minus tangent inverse 3 over 2. All right, tangent inverse 3 over 2 has no basic angle, has no special angle, so we can just leave it as trigonometry form. Okay, so that is how you convert from exponential to Cartesian or vice versa. Now, after dissing so much about Trigo form, we get this question. Z is root 2 EI theta. Theta is the argument, and it's from 0 to pi, inclusive of both. So it's either from first quadrant or second quadrant. By considering what formula is this? R formula. When you see R formula, which means that you have to use the Trigo form. Unfortunate. And R is a positive constant and beta is a non-zero constant, right? You see alpha, but since the font alpha sucks, I just use beta. And here's the interesting part. Find the exact value such that REZ and imaginary of Z equals to 1. Which means that why do you want to consider R sine theta plus beta in the first place? All right, so very simple. Okay, we're gonna use the Trigo form because we are going to use the R formula. So we consider everything as a Trigo form. We have real Z. So real Z means R sine theta. Just kidding. R cosine theta. Imaginary Z is R sine theta. So think everything as your theta form, Trigo form. All right, because the question wants you to do Trigo form anyways. Okay, so let's get to it. Let's get the R sine theta plus beta. Z equals to root 2. Convert everything to Trigo form. Just plunge down the Trigo form. Cosine theta plus I sine theta. Okay, now we get the R formula, which I'm gonna speed through. 2 sine theta plus pi over 4. Okay. Why do we do that? Very simple. Because we want to show that REZ plus imaginary Z equals to 1, we are going to get R cosine theta, which is basically root 2 cosine theta plus root 2 sine theta equals to 1. Okay? Yeah. Then we are able to convert everything together. So that's the whole idea. All right. I kind of messed the working a little bit. So that is the crux of the issue. All right. So, okay. So this comes from here. My bad. All right. Real Z is root 2 cosine theta plus root 2 sine theta. All right. Start from this equation here. That's how we got everything started. We know that the real of Z is R cosine theta. The imaginary Z is R sine theta. So we have root 2 cosine theta plus root 2 sine theta. We then have 2 sine theta plus pi over 4 equals to 1. Now we do the standard solving. I think you guys probably already know that theta plus pi over 4 equals to sine inverse half, which is pi over 6 or 5 pi over 6. Or do we need to consider the additional angle 7 pi over 6? Let me think. No. Do you? Yeah, you need to consider that as well. Okay, then whatever it is, you just take theta. No, actually, what am I doing? 7 pi over 6 is not an answer. Wow, I'm bad at this. Okay, so from here you just solve, then you get pi over 12, and then times 3 times 2, 7 pi over 12. Okay, so that's why trigonometry form is still kind of important, but I wouldn't say it's like the most important out of the three, right? It's actually one of the more useless ones. All right, so let me recap how we solve this question. Find the exact value of theta. It's basically our solving. So we have real Z, which is R cosine theta. So we have real Z from here, which is basically root 2 cosine theta. So this is real Z. Then we have imaginary of Z.
It is negative pi over 12, right?
Pi over, oh yeah, it's pi over 12. Well, then in that
Negative.
case, yeah, we can't have this answer. Yeah, too fast already, Lamau. Yep. So because we get pi over 12, minus pi over 12, we will then reject this answer because what's our original range of theta is 0 and pi. Yeah, my bad. Okay. Yeah, anyway, they say exact value, so we should send alarm bells ringing. Okay, so, oh wow, I actually give myself space to do that. Okay, so what are the properties of complex numbers? First one, I'm going to do everything in exponential form to show you how good exponential form is. Mod of z is again r, so I don't really need to go through that. Z conjugate, this is important, is REI minus theta. Why is that so? Z and Z conjugate. Let's say let's say your point is here, right? We label this complex number as A. Your argument is here to here, right? But now your Z conjugate or A conjugate would now be over here, right? Your imaginary is flipped. So what you notice, if this was theta, this would be minus theta, right? This is why your argument for your conjugate is the negative argument of your original complex number. Show you another. On the other side, you have, let's say, this point here. This is your argument. Sorry. This is your argument. So let's say we have alpha. Now we put the conjugate, which means your imaginary goes to the opposite or flips the sign. Now your complex number is now here. You notice that the argument is indeed the same, it's just that it's now negative alpha. All right, so think everything through the Argand diagram when it comes to argument. Okay, I'll show you more identities later on. For any real n, z power n is r power n, right? Because it's very simple, right? Look at this. All your indices rule, all your exponential rules also apply here. So z power n, you have REI theta power n, you get r power n, ei n times theta. That's why your argument is now n theta. Okay, argument is kind of like your log function, right? Where log, let's say x squared is the same as 2 log x, right? So it's acts as the same thing for your argument. So that's one way to think of it as well. Okay, so for any questions with z power n, use the exponential form. Imagine trying to use a Cartesian form or the trigonometry form, your paper will be super long, and you probably realize that, oh, I can't use Cartesian nor the Trigo form as well. Otherwise, on a very rare chance, you will need to use a Cartesian form, but I'm going to let you know that the question is going to be very different. They won't be using Zn anymore if you're going to use Cartesian form. Okay, so Zn stick to exponential form. All right, more identities. Z equals RI theta, W equals to KI phi. So if we have not a multiple of two complex numbers, your modulus will be multiplied as well. Your argument would instead be added because same thing, your exponent rule, right? You get RK EI theta plus phi. So this will now be your new argument. This will be your new modulus, right? So this is sec W. This is argument of sec W. Same thing for your divide. If you have z divided by w, r over k would be your modulus. Your argument will now be theta minus phi, right? Again, follow your exponent or your indices law, ei theta over ei phi, then ei bracket theta minus phi. All right, and these are the reasons why exponential form should be your go-to form whenever you express your complex number. Okay, now more identities and also showing you how do we apply some of the identities that we have learned thus far. Isaac and Z. All right, let's take a look at, let's say we have this complex number here again. Let's label this as Z now. All right, so if I apply Isaac, all right, let's say I give you a raw, let's do the Cartesian form first, right? We have 3 comma minus 3. So we have 3 minus 3i as z. Isaac would then be multiplied by I, right? So we get 3i plus 3. And then we notice is we get this one here. Okay. Now, the rotation, so this was your original alpha, right? Your original argument. You notice that we rotated by pi over 2. Why is that so? Very simple. If we look at the original idea or the exponential form for I, right? is I is right here. Right, it's directly on the y-axis or the imaginary axis. The argument for I is pi over 2. All right, so what I'm going to do is I'm going to rewrite I as EI d pi over 2. Now we have Isaac, so we multiply by Z, which let's say we give it as REI theta. Oh, whoops. And you notice we have Isaac equals to EI pi over 2 times REI theta, giving us REI theta plus pi over 2. As such, Isaac to Z is a Z to Isaac is a clockwise rotation of 90 degrees. All right, so let me illustrate that better. So you rotate by clockwise 90 degrees, sorry, counterclockwise by pi over 2 or 90 degrees, which means this angle is 90 degrees. This is a right angle. Same thing can be applied to our Z and minus Z. All right. So let's say we have this complex number here. Minus Z will be negative of everything. So you notice we get a turn of pi, rotation by pi. Why is that so? The modulus, or rather the exponential form of minus Z, we can rewrite minus Z as minus 1 times Z. Minus 1 we know is in the negative real axis, so the argument is pi. As such, we can rewrite it as EI pi times REI theta, which will then give us REI theta plus pi. It's a rotation of pi or 180 degrees clockwise. Okay, so we then have this question. Find the modulus and argument of 2EI pi over 3. Very simple. Answer is literally staring right at your face. Modulus is 2. Argument is pi over 3. All right, so modulus is right here. Argument is right here. Now it's slightly different. There's an additional negative sign. So what you need to do is, we know that we have REI theta. This is always positive. But now we have a negative, which means we have to do what we did for this one. Change it to EI pi, right? So convert this minus to EI pi, then you multiply it by 2EI pi over 3. Okay, giving us 2EI 4 pi over 3. But here's the problem. Argument is between minus pi to pi. So now we have 4 pi over 3. What must we do? Think of it as, what quadrant have we landed ourselves in? 4 pi over 3, so it's somewhere around here, right? Here you have pi over 3, because here will be pi, which is basically 3 pi over 3 plus another pi over 3. You now end up in the third quadrant. But because we are in the third quadrant, we need to measure our angle backwards, so negative. So this would be congruent to 2EI minus 2 pi over 3. All right, so 2 pi over 3. Put a negative sign there if you need. Okay, why the congruent sign? Because theoretically speaking, actually, yeah, because you now have a different argument. All right, your argument changed, so you should add a congruent sign. You see this congruent sign, I think you saw it just now. Probably see it again tomorrow. Okay. Now, if possible, use the identity as you learned just now about Z divided by W. What you guys saw we might do is, okay, let's do whatever we learned just now, 2 plus I times 2 times, rationalize the denominator and then try to solve. I don't recommend you do that, all right, because there's actually a quicker way to do it, which is basically the idea of Z over W as is shown just now. Okay, so very first thing you should do, convert this 1 plus I to a complex number. All right, so 2 over 1 plus I. So we want to find the modulus of 1 plus I, and then you find the argument of 1 plus I. All right, so give it a go. All right, give you a clue, leave the 2 alone. Okay, leave the 2 alone. And we 2 is going to be 2 lah, ultimately. Yeah. All right. So hope you guys got it. All right. 1 plus I, modulus is root 1 square plus 1 square, so root 2. What's the argument of 1 plus I? Basically, tangent inverse 1 over 1, so tangent inverse 1 is pi over 4. So we have EI pi over 4. Simplify this. So again, your basic indices law, root 2 EI minus pi over 4. Your argument, no, sorry, your modulus is root 2. Your argument is minus pi over 4. All right, so do not rationalize the denominator when it's very nice. All right, even so, don't even if it's a bad complex number, do not change it to Cartesian form, try to rationalize the denominator. Just directly find it, convert it to exponential form, or just do it, just find the modulus and argument. All right, so stick with this idea. All right, if you want to check your answer, all right, you can use a GC, type this, and then you realize that you'll get some very bad numbers, but you just need to put in your number again. This is basically root 2. By experience, this is basically minus pi over 4. Okay. Same logic for this one as well. All right, now instead of divide, I change it to minus. So again, just switch this to a complex number. All right, then you multiply by 2ei pi over 3. Combine them together, and then don't forget to convert or adjust your angle or your argument to the principal range. All right, so in this case, we already found what's 1 plus I is basically root 2 ei pi over 4 times 2 ei pi over 3. Okay, so you get 2 root 2 as your I, EI, pi over 4 plus pi over 3. So how I do it fast, 4 pi over 12 plus 3 pi over 4. Sorry, 3 pi over 12. It's just basic fractions, 7 pi over 12. And that is your answer, right, for your expressing this complex number. You can do it the normal way. If for some reason, if you want to do the expansion way, you get 2ei pi over 3 plus 2ei pi over 3 and then times I, but then, you then basically factorize this out and you get back the same answer. All right, so don't try to do this method. You can try. You're not going to have a good life. So just do it this way. All right, just take it to Z, W, change everything to your exponential form, right? Because that is the beloved form of complex number. The rest can go extinct. I don't really care. All right, now let's try this. Actually, we can just skip this because I think it's the same idea. You guys probably would have gotten it by now. So I'm just going to skip this. Now this one, again, change everything to REI theta and then kind of solve for P. Right, because they give you the modulus. Right, so I'm just going to give you guys a start, help you guys out. So convert the top part only to REI theta. All right, so top part REI theta is quite simple. Root 3 minus I. So take note of the quadrant, it's in the 4th quadrant. So which means your angle will be directly the negative of the basic angle. All right, so we have Z equals to, let's just put it this way. All right, so what you can do is simply just go root 1 square plus P square, or what you can just do is simply just evaluate the top part. All right, so root 3 minus I cubed equals to, experience tells me this is basically, okay, let's just go do the long way for you guys. 2 EI minus 1 over root 3. So tangent inverse minus 1 over root 3, or simply just calculate basic angle, tangent inverse 1 over root 3. That will give you pi over 6. Because you're in the 4th quadrant, it is the negative of your basic angle minus pi over 6. Then don't forget your cube. Thereafter, we have 8 EI pi over 2. All right, 2 cubed, then EI pi over 6 times 3. Pi over 6 times 3. All right, so minus pi over 2. Right, don't forget your minus sign. Leave it as the exponential form. Do not try to convert this back to minus 8i. All right, leave it as exponential form because you're going to find the argument of the complex number. But here's the thing. They give you that mod z is equal to 2, but then you have mod z here. We now use the identity that the modulus of k over w, wherever the complex number k over w, is simply, modulus of k divided by modulus of W. So we now find the modulus of W, right? Which is basically modulus of the bottom is 1 plus p square. Of course, because it's a square now, you have to do root and square, which is basically nothing. I mean, it's the same thing lah. Root times square will give you back the single one without the square root, power 1, basically. So we have the modulus of z being the top, which is 8, the bottom, which is 1 plus p square. And this equals to 2. We can then solve, right? So 8 equals to 2 plus 2p square. P equals to, all right, let me do it the slow way. 8 minus 2 is 6, 6 divided by 2 is 3. P equals to plus minus root 3. All right, which one do you choose? Well, usually the question will help you restrict this, but you know, just figure it out yourself. I think if I'm not mistaken, this is p bigger than 0. Yeah, something like that. Yeah, I think if I'm not wrong, p is bigger than 0. Yeah, p is bigger than 0. All right, so we can reject the negative root. So we get back positive root 3. So we need to add in the reason, reject because p bigger than 0. All right, need to kind of say positive real number. All right, then now you find the argument, because now you have the on top and you now have the bottom as root 3 minus I cubed over 1 plus root 3i. All right, then you can actually find the complex number for 1 plus root 3i. All right, actually the top you already have it. So what I recommend is change this to 8ei. Actually, you can take out the 8, so just put the 2 in front. Works as well. I pi over 2. Actually, no, you can't. Just leave it as. Yep. Then you find the argument for this, and don't forget this is whole thing square. So yeah, just convert that 1 plus 3 root 3i to your exponential form and then find the argument. All right. Now, why I speed run the last part is because that is quite basic. You just need to take your time. Now I want you guys to listen up. I know it's the last. No, this kind of overshot already. This became an accidental 2-hour lecture. But I want you to remember this part. All right. Why is that so? If you forget this trick, and if it does come out in the A-level paper, you'll end up in the same fate as some of my batchmates. All right, because this trick came out in my A-level paper, and many people forget how to do this. All right, so I want you guys to pay attention to these last few parts. All right, this is the last technique. First, I start with identities. All right, REI theta minus REI negative theta would give you 2RI sine theta or 2IR sine theta. So this identity is important because it condenses everything into one trigonometry. The proof is right here when I use the trigonometry form and some of the rules. This is one of them. The other one is REI theta plus REI minus theta to give you the same trigonometry form, one single trigonometry, but this time around it's not imaginary, it is now cosine theta. I want you guys to remember this down. Take this down. I mean, I will upload the slides anyways, but I want you guys to remember this at the back of your head, right? Because we have this question, or in fact, a variance of this. Let v equals to cosine theta plus I sine theta. And every time I see trigonometry, it irks me. I will change it to exponential. V equals to ei theta. Show that 1 plus v squared equals to 2v cosine theta. How are you going to do it? This is how you do it. Okay? We have 1 plus v squared, which is ei2 theta, right? Because ei theta square is ei2 theta. Okay? From here, you perform what is called the half angle trick. What do I mean by the half angle trick? You want to get the form of REI theta and REI minus theta, whether is it plus or minus. If you are to take out the half angle, which is 2 theta over 2, so which is theta, what you get is ei theta plus ei minus theta. And you can use this identity right here. So ei theta plus ei minus theta, I can write it down in trigonometry form for you guys to see. Cosine theta plus I sine theta. Here will be cosine minus theta plus I sine minus theta. All right. Cosine minus theta would then become cosine theta plus I sine theta will become minus I sine theta. And then we get everything together, we get minus of this off. We only get ei theta 2 cosine theta. From here, we know that ei theta equals to v. We then have 2v cosine theta. And this is the beauty, one of the main beauties of exponential form that many people underappreciate and forget. All right. The modulus and argument is very simple. In fact, it comes from here. Your modulus is this r here, just 2 cosine theta. So this would be your r. Your argument is simply your theta. And that's how you solve this question. All right. This question can go from 2 to 4 marks, depending on how, well, technically how generous they are, but apparently for my year, it was how sneaky they are. Okay. I repeat, this angle is called the half angle trick because we take out half of the largest angle when we have the form of r plus rei theta, because at the end, we'll get r ei theta over 2. We'll then get ei theta over 2 plus ei minus theta over 2. All right, and this would simply be 2 cosine theta over 2. All right, actually it's plus minus, plus minus, so it really depends. If you get minus, you get the sine version if the imaginary number. All right. Of course, there'll be some changes where you would get instead rei phi plus rei theta, where phi nor theta equals to 0. So there's actually some angle. So what you need to do is you need to factorize out, and then you will get this form again. Then you perform the half angle trick again. Alternatively, you can take out the average angle. So you can take out, let's say you have phi and theta, you take out phi plus theta over 2, and then you get you'll get back this form ultimately. All right, you get either ei theta over 2 plus minus ei theta over 2. That will be the form. All right. So for me, I call it the average angle trick, but in reality, it's called the half angle trick. All right. So last question of the day. I know it's been a long one. So show that rei theta over rei theta plus r equals to half plus half tangent theta over 2i. All right. Okay, let's do it. So we know that we can divide by r. So we get ei theta over ei theta plus 1. Right? Now we perform the half angle trick. Take out the half angle from here. Ei theta over ei theta over 2. Then we get ei theta over 2 plus ei minus theta over 2. From here, very simple. On the left, you get ei theta divided by ei theta over 2, ei theta over 2. Over here, you'll get 2 cosine theta over 2. All right, if it was instead minus, let's say ei theta over 2 minus ei minus theta over 2, you'll get 2i sine theta over 2. Of course, if we reverse the sign, let's say we get ei minus I theta over 2 minus ei theta over 2, we'll get minus 2i sine theta over 2 instead. All right, so again, depends on the sign, but that's not the point of the question here. All right, then from here, okay, very simple, expand everything. Because now you realize that the question they want you to get, or the form they want you to get, is in Cartesian form, x plus iy. So we now just simply expand. So we get cosine theta over 2 plus I sine theta over 2 over the denominator 2 cosine theta over 2. So we get cosine theta over 2 cosine theta over 2 is half. So that's 0.5. You can leave it as half plus I over 2. Then sine over cosine, same angle. That's why you get tangent theta over 2. And that is the half angle trick. And you need to take note of this. Okay. So that's the end for the lecture 1.